data infrastructure. And today he's going to be talking about reshaping data lake, Delta, Iceberg, Hudi, or Hive. Also for Eric, all questions will be answered at the end. And so we will go through all the questions at the end of his presentation. Eric, it's all you.
All right. Let me share my screen. Just give me 1 second. Okay. So can everybody see the screen share okay?
Yes, we can.
All right. So hope everybody is doing pretty good at home. So today's topic is something about how the data lake is changing in the recent years, particularly in the last year and this year. And there's a lot of interesting options in the market right now. So we're gonna spend the next 25 minutes to go through some of them. Today's topic, I want to talk a few things. Number one, this is not the first time you hear something similar to this one. And I'm just going to cover it from a little bit different perspective. Hopefully you can have some fun, get some, interesting story behind it, about why different options were shaped in a certain way and how you can make your choice at the end of, your own evaluation and moving forward. So a couple of things I want to mention here is like in the Spark Summit just finished about a month ago, there was a dedicated session talking about the comparison among, a Delta Lake, Iceberg, and Hudi as well. So I highly recommend you look into that if you want to find all the detail, right? Because today we only have 20 minutes. We're not going to talk too much detail about each, implementation detail, right? All right, so let's move on to the real thing. So before we get into the talk, I want to, go through a few, terminologies, and hopefully that will, make the presentation a little bit easier to understand. So the first one is called T+1 and the T+0. So this is some, something we often use to describe, batch, process or real-time process, right? T+0 typically means you can do a real-time or near real-time process. So your data insight was derived, after, 0 time when it happens, right? T+1 typically means you have to wait for a day, right? That's a very typical nightly batch. And in between we have hourly and minute batch. So those are the things, we are trying to move towards with the new technology and implementation of a data lake. We're going to spend a lot of time to talk about, these two concepts today, okay? The second jargon is called the Delta engine. I want to mention this is because this is very confusing, and every time you heard about it, you think this is something to do with Delta Lake. Yeah, they're related, but they're pretty much talking about two different things, right? Delta engine is a new computation engine, which is, not written in Java to speed up the, the Spark by about, 10 to 20 times. So if you want to find out more about this one, you can search for the, the talk about the Delta engine, or you can look at the Dremel. They have a very similar implementation, open source, you can try by yourself, okay? The next one is called skipping index, right? There's a lot of different, names for such index, but this is very popular, used in any columnar storage, and most of this kind of like, I would say, OLAP MPP system like Redshift, and this has a lot of usage to speed up your query performance. Okay, so we will see a few use cases here, and I hope we can get more understanding about how to make the best out of this kind of index in the data lake, right? DML is something it's pretty straightforward. Just want to mention here. Time travel is an interesting concept, right? This is not about science fiction. The time travel here is really about how to access the different snapshot version in your, in your data set. This is more of the transaction control or the ACID, and also, but the time travel is more about the access part of, so how can you ping your reader to a particular version of your data. This is something I think a lot of machine learning people are very interested. So we'll spend a few slides talking about this as well. Right. The next one, SCD2, right, stands for slowly changing dimension, type 2, right? This is a very old school concept, but we'll probably will mention it a little bit today as well. So the next one is called object store or cloud storage. This is a very typical about, when you move to cloud, you no longer use, your NFS, DFS, HTFS, you're using something called object store, okay? There's a lot of reason for the data lake, technology we're talking about today, because they try to overcome some, limitation of the object store. Okay. The last but not least is about streaming and batch unification. That is one of the core reasons that all this new data lake technology come in place, because the goal we try to achieve by doing this. All right. So before we go into the new architecture, let's just take a step back and have some reflection about where we came from, and also about all this different terminology we have been dealing with in the past like 15, 20 years, right? What are they, and how different they are? So often we heard about data warehouse, this is the old school. And then we were talking about data lake in the past probably 10 years. And then we're, kind of like moving to some new thing about, lake house, data lake V2 or something. I'm not going to go through each, item here. All I'm trying to do here is try to say, all these three things, they're actually the same thing. They're just different implementation to solve the same problem. That's why, today, my presentation is going to talk more about the commonality about, people try to solve the common problem instead of trying to give you the nitty-gritty differentiation about all this terminology and throw you into the different track, right? We want to see the common pain point and how people to address them. You can refer to this presentation after the session, and you can go through all the detail, and I'm happy to kind of deep dive and answer any questions offline about this one, okay? All right, so we want to talk about some of the common goal that we try to achieve, no matter you call it a data lake or data warehouse, or whatever fancy name you want to call them, right? So here are a few things we want to talk about. Some of them, in the past decade has been really misled by the marketing campaign by different vendors, because they kind of like say, oh, schema was not important, we should go all to schema-less, right? ACID is not important. But after about all these years, we finally realized and agreed again, and all these matters, and all these are very important concepts, and we should have them in our data lake. So I listed a couple of them here, and that's why, some of the, technology we're going to talk in the next, 15 minutes will represent how they try to bring some of these, characteristics of a data lake back into reality instead of simply abandon them, okay? A couple of things we're mentioning here is about mutable, right? This is some of the very important concept we're going to talk about today, right? You may feel like surprised, like, data lake is supposed to be read-only and write once and read 1,000 times. What is this mutability coming from? And I will definitely spend some time to talk about that, right? The other one is, do we still need SQL, right? Do we want to still support the relational operations such as join, aggregate, materialize view, and caching, and all that kind of stuff, right? I think, we will walk through a few use cases from the different companies and explain why they still matters, and we should even care them more than ever before, right? The other one is, everybody wanted that, your data lake to be fast, but should we oversimplify the fast to support only a simple model or pattern? Or we should really rethink about how to build a faster data lake which can support multiple access pattern and usage pattern, right? When I say multiple, it means could be streaming, could be incremental, could be quick and small, could be big and big and large. Could it be scan centric? Could it be lookup centric? Could it be aggregate centric? Could it be multi-version? Those are the different patterns we're talking about. We want to make all these patterns fast instead of just trying to say, okay, I only want to do key value pair, that's it, and I will leave everything else to the user to figure out by themselves, right? Okay, so this is a template slides. This is not really a detailed design, architecture diagram for any particular company or implementation, right? So as you can see here, there's a lot of placeholder or multiple option for the section, but this is a typical landscape we use to describe the solution scenario. On the left is the source. You have multiple source, and you use some ETL or streaming ingestion to bring this data into your analytic system. And typically, you can use, Flink or Spark, that kind of a processing engine to load them into your data lake area. The blue box in the center is more about this data lake, or no matter whether it's a V1, V2, or data warehouse, right? That's the area we want it to be. And the goal is here, and can we unify the, between the streaming processing or real-time processing and the batch processing? And I think, simply answer the question is, of course we want to do it, but the question is, how do we do it? And how close we are to that, or is any big obstacles that we have to overcome, right? So if we have a unified data lake which can support both near real-time use case and the batch process at the same time without stepping onto each other's toe, and then that will be really awesome for us to power all the applications and use case on the right side, right? From advertisement and machine learning and A/B testing and all this, kind of metrics, reporting, all that, right? So what I used here is something like I talk about, like T+0 means really like a real time, without any delay, or with a couple minutes delay. And these are all considered as, a real time. When I talk about this, I want to mention some, kind of like a side box here called Druid. So this is typically used as of today as the near real-time analytic engine. That means all the data coming from Kafka or other streaming sources will be loaded into Druid first. And from there, you can do the near real-time analytics with very little latency, okay? But going forward, right, a lot of, you still have to maintain your data in your Hadoop, in your S3 for the big batch, right? Because you want to go beyond the 7 days, you want to go to 3 months, 1 year, 2 years, and you need to do a lot of join, all that kind of, operations. And you cannot do it in a Druid or Pinot, that kind of a near real-time analytical store. So you still have to do that. So the new data lake architecture is really trying to simplify this one to say, okay, we don't need those intermediate one, and then we can get everything solved in this unified, data lake. so that it can also work on the T+1 and the T+1 hour or T+2 hour kind of a scenario. And in that way, and all the innovation were happened in this 3 categories plus the computation engine, right? So you need a new data format, and with efficient SERD, a library, and then you really need a new table API and a advanced, metadata catalog, right? So in the next couple of slides, we're gonna start to go through some of the options. You guys probably know the name, and maybe you're using or trying or doing POC in your own company already. Let's go through them. So here is some of the reason, like Netflix, Uber, and the Databricks putting forward the new solution, right? So let's quickly talk about the problem, like so that when we look at them, we can understand it better. So the first one is, we want to talk about the object store, right? Object store is very popular. There's no question about it, but it is not a file system, okay? Today, the majority of computation engines from Hadoop, Hive, Pig, Spark, and they are all designed to deal with a file system as a first-class citizenship. And then later, they added support to the cloud storage, AKA object store. But their support for that is kind of like evolving gradually to reach the maturity. And during that time, we find certain limitations that we have to overcome, right? One of the reasons I want to talk about here is about how do you trade between scalability and the function rich, right? S3, Azure Block Store, and GCP, they all have very, very scalable object store. But these object store, they are cutting down some features so that it make it very, very scalable, right? But then our computation do need some of the other functionalities. That's why today, the data lake implementation is trying to fill the gap and re-implement some of the patterns and operators in the data lake layer instead of using the storage layer to fulfill those functionality, right? A few things we talk about is between REST and RPC, right? You guys probably know that HDFS was mainly implemented based on the RPC, and Web HDFS is the only thing you can use as a REST API interface. But going forward, that support will become less and less important. But if you go to S3 and everything is based on REST, which is very easy to program, but one of the biggest pain is during the planning time, right? The planning time is very chatty. When I say chatty, means you need a lot of small, REST calls to get a small amount of metadata back and forth from your storage layer so that you can plan your job properly, such as, how many files you need to access, where is the offset you're gonna split for each, map, reduce, or task to handle. And how do we make use of the skipping index, right? To make your job more performant so that you can skip as much unusable data as possible. Or where do you find your columnar a segment, right? Because you don't need all the columns. You only need, a 5 column out of 500. So how do you do those kind of planning? But then this imposed a lot of pressure on your typical cloud storage because they were not designed to handle this like a little very chatty access pattern, all right? But to make it correct, all these problems are being resolved and addressed gradually as the usage of cloud data warehouse or the cloud-based data lake becoming more popular, right? So this is a moving status. More and more new APIs have been made available to address this issue. But as of today, if you guys were, your company are running a data warehouse on the cloud, this typically you will also, spin up your own HDFS cluster as a, temp or intermediate layer, right? On top of a whole bunch of VM, which is doable. But it's extra, maintenance and operational burden for you to keep it up. And do you shut it down after a couple hours, or how big is your HDFS? Because HDFS is not very easy to kind of like a scale, add any machine on the fly, or something to tear it down, because you need to back up your data or the stuff. So you can still do that, but then the new data lake technology will help you to see if there's a way you can simplify that without doing your own HDFS on the cloud, right? Okay, so the next one is very interesting. It's about a metadata itself, because the metadata by definition, we always have the impression the metadata is small, right? The metadata is about the table name, table format, and maybe a few, table property. I'm thinking about a couple of, lines of a metadata should be enough, right? But the thing is, if you want to improve your query performance, then you cannot do the full table scan and the full, a data file scan all the time. Because eventually, if you do that, your storage is still relatively cheap, but the bill for your computation cost will skyrocket, right? And then you need to come down and say, okay, I need to use columnar data format. I need to use partition. And what else can I do to improve my query performance and save my computation cost, right? If you want to do that, you have to do something else. Means you have to provide more metadata so that your query engine and the computation engine can make a wise decision. And once you go down that path, and suddenly you realize your metadata becomes bigger and bigger. Okay, so this is one of the problems that Hive is trying to move from its relational backend to HBase a couple years ago. That attempt to reflect this problem statement, even though Hive didn't really finish that, and that mission has been picked up by all this like Uber, Netflix, and Databricks, and they want to reinvent this in their own way, but try to address the same problem. All right. Okay, so last but not least, mutable and immutable, right? I'm going to skip all the detail, but one point I want to make is today, if you want to build a data lake, actually you need some level of immutability for your data, right? If it's for GDPR, IDPC reason, you need to delete the member records, right? But for streaming and the batch unification, then you really need a very strong incremental processing mechanism that can keep loading the new data into your data lake without affecting the batch consumer or other streaming consumer, right? They will not read the dirty data, and they can read the incremental, the new data very easily without reprocessing the historical data they've already processed. All this need to make data lake really mutable, right? But you cannot really build immutable things easily because your storage layer as S3, they are not mutable at all. So you have to invent some mechanism in between, which is your data lake layer, to implement this pseudo or the virtual mutability. All right. And now let's quickly go through all the candidates. We're still trying to solve all the problem, right? Don't forget Hive. Hive is still in the game, even though the Hive's importance has become less and less as it happens now. But Hive is still very important because Hive still set up many standards for the industry, right? So Iceberg is something created by Netflix, and it has a very strong, I would say, preference to solve this cloud-related problem, okay? And the Delta Lake, of course, it's coming from Databricks. So the number one goal here is trying to make Spark better, right? So no matter you run Spark on the cloud or on premises, or no matter you are using Scala or you're using Python or using Spark SQL, you know, Delta Lake is trying to make your Spark experience more productive and the Spark job runs faster. So that's their goal. And the Hudi was invented by Uber, right? Uber is really focused on the performance of the mutable data, right? So you can see a lot of the details and you know, a trade-off they are making reflect that kind of a goal to make the mutable table really, really awesome. Okay, so now first we're gonna talk about Netflix, right? Netflix is heavily, is 100% on AWS. That's why the data lake solution provided by Netflix has a lot of, you know, deep thinking about how to make the cloud storage better, including how to avoid a rename because, you know, S3 doesn't have directory structure or the rename operation. So the only thing you can do is try to avoid it, because no matter how you're gonna mimic the rename, you're gonna, you know, suffer the overhead, right? The other one is how do we speed up the query planning session? So that simply said is how do we gather all this metadata that we need for efficient query planning out of the Hive and put into Iceberg's own control, right? So that's what Iceberg is doing, okay? One of the things I want to highlight is today, Iceberg does not have the DML or the you know, delete, update, upsert implemented yet. There's a reason for that. It's not because this is not needed. This is probably just not as urgent needed as other features by Netflix, because Netflix has a pretty big, you know, Cassandra infrastructure. So a lot of their kind of lookup kind of a use case can be handled by Cassandra already, so that they kind of deferred the implementation of the DML feature. You know, so this is the Iceberg currently is the only one out of all these, you know, 4 options who has no DML implemented, but their pull request and the design doc has been there for more than a year already. So I'm pretty sure DML will be made available pretty soon, okay? And the last is Iceberg is a very open design data lake implementation right now. When you compare that with Databricks Delta Lake, you will see a very significant difference, because this is not tied to a file format or the computation engine. From day one, they're thinking something very independently, okay? So let's talk about Delta Lake, right? Delta Lake, you know, I'm gonna show you a small slide in a few minutes. And what you can see is, you know, if you are a data scientist or a data engineer, when you see those examples, you're gonna say, wow, this is exactly what I need. This makes my life so much easier, okay? So that's how I feel it too. But if you are an infrastructure engineer who wants to build the platform and infrastructure, you may have some doubt about maybe that is too much, you know, integration with Spark itself, right? And it's not very open. It is also open, but it's not that open compared with Iceberg. Then you may have your doubt about, you know, which one you should choose. We're gonna talk about that later. One more thing I want to mention about the Delta Lake is, when I look at the Delta Lake about a year ago, it seems like, you know, a good concept, but not, you know, not many things were tangible or usable yet. But look at their release, you know, history from last June to now, right? Every release, they add some critical functionality. And because of the user base of both their paid customers and open source Spark community, and most of this, you know, functionality were widely tested, and they're in pretty solid shape. And so, you know, last month when we look at the Spark Summit, you suddenly find, you know, Delta Lake was at a much better shape than ever before, and it seems like, you know, it has all the functionality you can use. You know, and you should be able to, make your own POC with a couple of days for a lot of use cases already, right? That's really exciting. You should pay attention to that. Okay, so let's talk about Uber's Hudi, right? Hudi is actually less known than the other, 2 or 3 options on the table, but Hudi was also widely adopted by the company who has a lot of this kind of dimension data or, near real-time analysis, which kind of like fit into in the Druid, place, right? So you have a lot of, a multiple source, you want to ingest them to Hadoop so that you can do the mini batch. The mini batch is typically like 15 minutes to 30 minutes latency, right? You want to see the insights, metrics, aggregates, and all the report with only 30 minutes latency. Then that's why Uber created this one, because Uber's, the Uber Eats, Uber hauling business, they need a lot of, immediate, quick, aggregated insights about how the marketing is shifting and where's the demand, where's the supply, all that kind of stuff, right? So that's why they actually build a lot of, optimization to do this incremental processing, okay? It supported delete, update, upsert, and it also has different ways to do the delete and to do the upsert, right? There's one thing called copy on write. This is the most popular one, which is used by, other, Delta Lake as well. But there's another option called merge on read, right? This option is used by Hive and Uber only, Hudi only. And one thing I want to mention about it is Uber is very committed to Flink as well as Netflix. So this will actually become some of, anecdotes we're going to talk about when we think about the competition or the moving forward landscape about all this data lake technology. Okay, keep that in mind. I'll get back to that later. Okay, so quickly,
Eric,
yeah.
A quick interruption, just so you know that we're approaching the 5-minute mark.
Sure.
So just
Okay.
to let you.
Yeah, so we have some examples of the code, and I will not spend too much time about it, okay? You can take a look at them a little bit later. So I just want to quickly touch base on the time travel, right? Time travel here is based on what you, in the reader part, and you can actually specify a particular snapshot of version that you want to access, right? So this is really useful for you to kind of go back to the time. But in all this implementation so far, you can only go back 7 to 30 days, or you can go back to 60 days. But you cannot just change the granularity. You can go to say, okay, after 7 days, I can only go back on the per week basis, or after 6 months, I can only go back to per month basis. Because in a lot of a real world use case, when you go back further in time, you don't really need the, up to, our granularity or precision about this one. That's why, currently all the time travel feature provided by the data lake technologies really try to unify the streaming process and the batch. They're not really for the machine learning feature regeneration that go back all the way back to 6 months ago or a year ago, okay? Unless you really keep a lot of, history log there, all right? I will skip some of this about, what else is missing in this data lake implementation, because, I believe most of the company hasn't really moved on to the new data lake infrastructure yet. So this is really future looking, but we can definitely talk about it later, right? So now let's talk about, the choice, right? How do you make a choice out of this 4 options, right? That is typically hard, right? Right now it's like you have too many options. You don't know which one is better, which one you should pursue. That's why I want to mention a few things here is the Delta Lake definitely give you better support about your ecosystem means your developer system, because if you have a lot of people using Python and they use Spark writing ETL already, so then using Delta Lake could give you a lot of a less learning curve, better integration. But the only thing you should keep in mind is you do have that locked in, means you do everything in Spark, right? If you don't like certain, if you have a use case which Spark cannot solve very well, then you probably have to kind of rewrite some of UDF or the function in Spark to address it, instead of just switching to another application or platform, right? Which has built-in solution for that problem, right? So that's the only caveats you need to keep in mind. The second point is the whole Flink community is all in for Iceberg. So when I say this Flink community, including Netflix, kind of like and Alibaba and Tencent, ByteDance, and a lot of this Chinese company, gigantic internet company, they're all kind of like using Flink. At the same time, they try to use Iceberg as well. But at in Bay Area, you will see like Apple, LinkedIn, outside the Netflix are kind of using Iceberg right now, right? The third, but not the list, is all these big guys like BigQuery, AWS EMR, Synapse from Azure. They all kind of support all these formats: Hive format, Delta Lake format, Uber, Hudi format, and Iceberg format. They support all of them. But that didn't really tell you much about out of these 4 options, which one is better, because they support all of them. But the only thing is you need to keep in mind is they are selling you the computation engine, which is the query engine itself. So that's why they need to support as many formats as possible, right? Okay, so I think I'm approaching the end of the minute, so I have a few further readings for you guys, and these are very interesting things to give you more insight about what else is missing and how we can make better use of all this new data lake technology. All right, okay, Sarah, Sam, goes back to you.
Thank you. So right now, this is a perfect time for people to ask some questions. If I have questions for Eric, just please enter it in the QA and we can answer them. While we're waiting for some questions to come in, Eric, if you wanted to go back over one of the slides that you skipped over while we get some questions coming in, I think that's fine. I just want to make sure we have time for questions.
Sure. I think the last slides, we'll just keep it here, is about, I think, a lot of you guys come to this session is because you want to get more insight about how do I make the choice among all these 4 options, right? I don't have a holy grail for any of you, right? All I have is, don't wait for the single best choice in the market, because as I said, each company come up with their own data lake solution to solve their own pain point, right? And then you need to think about your pain point. Do you have the similar pain point than like a Netflix or Uber, or or you are a pure Spark shop, right? So based on that, you can make your first choice about which data lake I'm going to go first. But if, let's say, you do have heavy use case about a mutable table, or a pretty low latency or high SLA expectation about near real-time analytics, then you should also choose that one just for that piece, right? Instead of say, okay, my data lake has 2 options. One is maybe Delta for the general table, but then for the near real-time, I can choose Hudi for now, right? So you can also go with that. That's what I mean by a combination of 2 options together, right? And then once this all the technology evolved to the next level, then you can do some migration because you have to do migration every 3-4 years anyway. So don't just wait for the best choice. That's what I'm trying to share with you. All right.
Oh, that sounds great. There's one question which has to do with the slides and when they will be made available. One note is the recording will be available soon, but the slides on their own?
Okay, so if you want to visit the slides, it's already made available with the this link. It's a SFBA 0728. Yeah.
Beautiful.
Yeah.
Thank you. This is great. Here at Salesforce, we also have a data lake. So it was interesting hearing you talk about the same sort of problems and things that we're struggling with on our own data lake, like doing the batch and the streaming and everything else. So this was a really fascinating talk. If you have other questions, we may have time at the very end of everything. But for now, it's time to, whoops, I should be sharing my face, but that's okay. It's time to switch over to our second talk, which is being done by Lituan Pei, and he's from PingCap. And he's going to be talking about HTAP databases and how they can simplify your data infrastructure. He is a senior software engineer at PingCap, and he focuses on database kernel. So it's all you.
I got muted, but can you see my screen?
Yes, we can see your screen.
Cool. Yeah, it's an honor to be here and talk about HTAP databases and share some of our insights on how can they simplify your data infrastructure. So I'm Li Kuan. So I'm currently a database engineer at PingCap and based in San Mateo. And if you, the PingCap is actually the company behind TiDB, it's HTAP database. And in this talk, I'll be talking about how an HTAP database can simplify your data infrastructure by going through some of internals and also some of the challenges of building an HTAP database. Continuing to Eric's talk, is really, I think there are likely two trends. One trend is like the big data solutions is adding features from databases like the transactional ACID properties and supporting updates, right? So that is one trend. On the other hand, for databases, they are enhancing their analytical capabilities to support more diverse workload. And I think I want to take this perspective and in my talk and share with you our vision of the HTAP database. So what is HTAP database? HTAP is short for Hybrid Transactional Analytical Processing. And it was introduced by Gartner in 2014. And it's as the name suggests, it just describes the ability to process both transactional and analytical workloads, right? Sounds simple, but in practice is pretty challenging. And I'll share with you those challenges. So before I before talking about HTAP, I want you to kind of like talk a little bit about a typical data infrastructure, and this can be familiar with you. I think this is a typical data infrastructure used to power many modern data-intensive applications. And I believe many of you have used them on a daily basis, like Uber, Lyft, or all the social networks like Snapchat, things like that. And really, there are three tiers in the data infrastructure. The first one are the services and data that's supporting the application, and we call it the business layer. It's composed of like relational databases and non-relational databases. And the second tier is really the real-time layer. And those are the ones we use for the real-time analytics. Usually they are using Kafka, and we use a stream processing engine to do real-time computation. And the result usually sent to a database or a NoSQL database for serving the application. And the third tier is the offline layer, which typically we save the aggregation or the historical data. And that are usually for machine learning applications. And people, we usually look at the historical data and do a model training. And the result also be used by online serving layer or by some other query layers to provide like insights over historical data. Yeah, actually this infrastructure actually works, and it already powered many applications we use on a daily basis, but there are a couple of challenges to that. And why there are challenges? Because there are two categories of applications really in this diagram. One, I call it are the transactional databases or operational databases. And those are databases or data systems are used to support the online applications. And those are usually called the transactional workload. And the other one really is the analytical database or analytical system. They are used for analyzing the database, analyzing the data. So the challenge is really that the TP system, the transactional system, and the AP system, which are analytical system, they have very different design goals. For example, if you want to analyze online order data, actually usually, as the figure shows, you need at least two systems to do that, and you need to build the ETL or data pipelines between them to copy over the data. And the data copy is expensive, especially for large data volumes. And another challenge is really like we copy the data not because of the business needs that, it's really because of we use different systems. What is worse is like inside each system, we design the system to be highly available and fault tolerant. Therefore, multiple data copies are stored inside each system, and this makes the overall more costly for your company, because actually you stored more data copies than actually needed by the business. In summary, really like for modern data for current like data infrastructure, we use a set of tools together to accomplish the business goals. Whereas if you have a single system that can do both transactional workload and analytical workload well, you actually like it's more like a Swiss Army knife, right? That can do multiple things really well. And the second thing is that for doing those ETLs, it's challenging to keep the data fresh. As mentioned in Eric's talk, typically we do T+1 or T+hour, right, or T+minute. But sometimes really this ETL process can take a long time. Basically the result we see is actually from yesterday's, you're really looking at not the fresh data. What we really want in some cases is like, we want to look at the data as the data arrives, which we want to look at the fresh data. The third thing really challenges is that it's really hard to achieve consistency in multiple systems, especially strong consistency. There are always slightly delay or slightly differences between for the data in different systems. And so for most of the systems, we can aim for eventual consistency, but you want to support strong consistency, and that will be challenging. And I think those are kind of the motivations behind HTAP. It does offer some like kind of like if we can have HTAP databases, then we don't need to have the ETLs, and we can really analyze the fresh data, and we do have strong consistency. And that's are the benefits of the HTAP database. So, but those are challenging. And we want to talk about those challenges by analyzing why a transaction database is not good for analytical workload. I think let's start with the format, right? Typically, a transaction database is using row format, and which is good for like point queries, whereas or short range queries, you can use index to look for a certain record, and then do a linear scan to get the following records. But actually, it's much more performant if we can store the data in a column format for analytical queries, because analytical queries is usually work on very wide tables, has many columns, and they usually want to look at subset of the columns. And also the data is usually scanned through a large range instead of like a point queries. And because those low workloads are very different, and column store is really a good format for analytical workload. And also we can do column pruning using columnar store, which is not possible for row format. For example, if you want to do point query, the row format can be very fast because you can really use an index scan to find this, to locate this record very fast. But for analytical workload like doing aggregation, what we really want is we can quickly read all the rows for a certain column and then perform the computation. Another challenge that causes the HTAP to be hard to build is that there's usually a interference or between the transactional queries and analytical queries. Because they have different design goals, and the analytical queries usually optimize for fast response time, which means that we want to use all the available resources in the system so that I can return the result in the shortest amount of time. Whereas for transactional workload, the goal is to support large number of transactions and low latency queries. You don't want a single query to occupy all the transactions. If the system doesn't design right, a heavy analytical query can exhaust all the resources available on the cluster, and then the transactional workload get impacted. And as a result, your application get impacted and may not meet the SLA. So this is not what we want. What we want is that the transactional workload and analytical workload can be handled in separate resources and provide isolation between them. And here comes how TiDB solve this problem. And this is the high-level architecture of TiDB. So I want to briefly talk about this architecture. So the TiDB has two major components. One is the computation layer, and we call it TiDB servers. And we also have two storage engines. One is the TiKV, and the other is iFlash. The TiKV is a row format, and it's basically, we use that to handle the transactional workload, whereas the iFlash are the columnar format, whereas we use them to handle analytical workload. And I want to dive a little bit more on that, because inside TiKV, the data is divided in regions, and each region is logically can be viewed as a contiguous key ranges. For example, if you key ranges from 1 to 100, and each region will take from 1 to 25, then 25 to 50. They are range partitioned, and each region is replicated, has multiple replicas, and they are maintained as consistent using Raft consensus algorithm. And also we extend the Raft consensus algorithm to replicate the data to the iFlash nodes, whereas the iFlash nodes is not a leader of, is not a follower to the system. Yeah, I'll dive this later, but one thing that makes really good is that we ensure that the data available in the iFlash node, which are the columnar format, is strongly consistent with the row format. And this will give some nice property, like for each table, you can really, you can not only look represented by the row format, but also the column format. Okay, and here we also have our extension called TiSpark. And this is how TiDB integrates with the Spark or the Hadoop ecosystem. And I'll talk about that in the following slides. And to sum up, and the TiDB is a compute and storage disaggregation architecture, and it has a column engine and row engine, which are optimized for both the transactional workload and analytical workload. And in the later slides, I'll talk about how to make them the internals of the architecture to make sure that we can achieve the strong consistency between row format and the column format, and as well as the resource isolation between them. Okay, so if you want to know more about this, more details about how we build the HTAP database, we actually have a paper published in VLDB this year, and it should be available soon for download. And we also expect to have a publication or presentation in August. Okay, now let's talk about TiFlash. TiFlash internals. Okay, as I mentioned that we have a row engine called TiKV, right? And TiKV is a transactional key value store. And there are many things we have done to make sure that TiKV can handle distributed transaction well as support isolation levels and high frequency updates. And this is actually our main benefits of TiDB. And then that actually helped many users to adopt TiDB because we can really support the SQL capability or a database capability in a distributed fashion, and can grow their business by simply adding more instances to the TiKV nodes and the TiDB nodes. What we do is that the interesting part here is that it's a relationship between the row engine and the column engine, right? How do we make sure that the data between them are consistent? As I mentioned, the TiKV is using Raft to do data replication. So Raft has two roles, leader and follower. And the leader is an entity that accepts both the read and the write operations from client. And one challenge is, for the Raft, it's really a column-based replication, which means that operational command has to be accepted by the quorum of the followers in the system. In this case, if we want to make TiFlash another follower to the system, then the TiFlash actually will have some interference to the TP system because all the followers can become the leader, right? So that will have some interference. To avoid that, we're actually not using the TiFlash as a leader. We're actually using Raft, TiFlash node as a Raft learner. The learner node has a property that it will replicate data from the leader, but it will not become a leader. It will not participate in the leader election process or the data replication or the acknowledged processes by the follower. As a result, the data copying to TiFlash will not causing a latency sending back to the client. And but then another interesting problem is that how to make sure that the data is actually consistent, and we'll talk about that later by using some properties of the Raft algorithm. And during this algorithm, during this sync between the TiKV and the TiFlash, we actually transform the data from row to column, and we've also making sure that the schema information is copied over to TiFlash. And so that is used, the schema information is useful because if we want to store the data in column fashion, we actually need the schema information. Okay, here are some highlights of the features. So TiFlash is a high performance, real-time updatable column storage. I think one difference of the TiFlash compared with the data lake solution is that it can support high frequency updates. I think the data lake solution can support probably high frequency append or insert, but it become challenging to support updates because the underlying actually data supporting the data lake is immutable like S3. So if you want to do updates, you actually need to do a lot of like changes to the different places, different files. And as I mentioned, we also extend the Raft algorithm to include learner role, right? And during the read time, we use some Raft algorithm to make sure that the data read from the TiFlash node is strongly consistent and transactionally consistent with the data in TiKV. And for this architecture, we actually extend the capabilities of both the transactional database and the analytical database. And for the transactional scenarios, we actually can support real-time analysis over their transactional data. For example, for some logistic companies, they do want to see the delivery rate in real time. And for Uber, they do want to have their ETAs like in real time so that they can provide their service better. And then that scenario really like we add a capability. And the other part is that for AP scenarios, we can analyze the data in real time and to reduce the latency and improve the data freshness.
Before you go on, we actually do have a question. If
Yes.
Like.
Yes.
And this is from Hamid. Is replication from iFlash to, I'm going to pronounce it wrong, within a transaction as well? Can I update records and then run complex queries on column store, which
Yes.
must be my update? That's
Yes.
all within the transaction. So the answer is
yeah. Can you repeat the question? Yeah.
Is replication from iFlash within a transaction as well? Can I update records and then run complex queries on column store, which must see my update? That is all within the same transaction.
Yes, they are strongly consistent. Once the okay, so basically TiFlash TiKV has the same isolation level, and by default, they are snapshot isolation. By which I mean, once a transaction is committed, and then when you issue a query, let me take it back. So every read or write query, it will be inside the transaction, which means that even for a read transaction, a timestamp or transaction ID will be a unique transaction ID will be assigned to that transaction, and based on that transaction ID, you actually get a consistent snapshot by reading either through the TiKV or through TiFlash, and from there you can actually reason about the correctness of the actual isolation levels.
So to a quick follow-up related to that is, if you abort it, do you unreplicate those records? So, and it sounds like, correct me if I'm wrong, the answer is this is all within the same transaction. But if you abort, do you unreplicate? And is that a fair translation of what you're asking?
Can I see the question?
Of course, please go look.
Yeah, I cannot have it open. Okay, what's the same within the same transaction? Okay, so let me see this. Okay, so for the uncommitted transaction, okay, so all the transactions are ordered by the commit timestamp. If the transaction is not committed, it's actually not visible by the other transactions. That make sense? Okay, basically, it depends on, okay, so you can think about this way. So each transaction has a unique transaction ID, and this is how do we order things. And for a transaction that is not committed, it is it's not available for concurrent transactions. Yeah, I think that is how the transaction works. If it's abort, this will not be reflected by the other transaction. So I cannot see the result in my update. Yeah, okay. So okay, let me see. So for the same transaction, it is visible. Okay, okay, I see your question now. So for the same transaction, it's actually visible because when you read the data using the column store, it's actually because from the TiKV to TiFlash, it's actually asynchronous replication, right? But when we read it, we actually use a method called read index, which means that we'll wait for the replication to caught up before we return the result. Then it actually can read in the same transaction. This answer your question? Okay, if there's no further questions, I will proceed.
Yeah.
Okay, so because it's architecture, it's actually okay. I'll answer that question later.
Yeah, why don't you continue, and then we can go into more details at the end.
Okay, sure. So basically, because the column provides better optimized for batch scan, and we also use leverage ClickHouse to provide vectorized execution, so to speed up the query. And we do have a different design for the storage engines for the column store and the row store. For the row store, we use RocksDB, which is underlying a LSM tree. And for column store, we design a system called storage engine called dirt merge tree, whereas the data is divided in ranges, and we use B+tree to index those dirtas. And the nice thing about this, during the read time, there is actually less read amplification, because for LSM trees, because their keys are in different regions, you have to scan multiple layers of data, and you have to read multiple data because you don't know where the latest data for a certain key. So you have to read multiple layers. Whereas you only for the dirt tree, you can do a quick a pruning based on the key ranges, as well as you only need to merge the dirt spaces, which are kind of the accepting the writes, whereas the stable stages, which are immutable. So you have less read amplification here. And also another thing that I mentioned, we have using vectorized engine. So any processing is handled by a batch of entries inside the column, so to speed up the process. And based on this design, actually for iFlash, we can query on the latest data, not just fresh data. So the way we make sure that the data in TiKV during the read time, the data in TiKV and the iFlash, they are consistent. And because this replication is actually asynchronous replication, so there's really very little interference between the TiKV cluster and the iFlash cluster. And then, which means that compare this with the ETL, this can actually very low. There's actually no close to zero delay between the iFlash node and TiKV node, whereas the ETL, there has to be a couple of steps there, and it's hard to make them like very low latency. And how do we do that? We actually use rough learner and rough leader to do that. So basically there are two things, right? One is that to make sure that the data read by iFlash is consistent with the rough leader, which are the data in the TiKV, we're actually using a read index, which means that we'll wait for data to be copied, to be replicated to the current position, so that we can return. So because of for iFlash queries, for queries over iFlash, actually we usually read a large amount of data, and a small amount of wait will not incur big latency overhead. And also because of this, and the iFlash nodes and the TiKV node actually physically can be placed on physically isolated resources. And there's kind of isolation and low interference between them. And yes, because the iFlash is a learner, and they can read them. They can read them, and they can. Another thing of important, another benefit of this architecture is that we can. It's really like we can combine the power of both. The benefit of both the TP solutions and AP solutions. Because the iFlash is strongly consistent with the data in TiKV, right? You can think about iFlash as a special index. It optimized for the scan. And also the row index, they are optimized for point query. And usually that you can actually use TiDB as a unified engine to query both formats and compare the both format in a single query, right? And sometimes you do need this. For example, for logistic data platform, you need high concurrent point queries on package details and customer info. We also want to have like sub-second analysis, such as arrival rate during a certain period of time. And if we have strong consistency between the data, actually it makes building the application easier. So for example, for this query, we do have a point query to find a batch ID, and we do have a scan query that are joint data between the product and sales. So, and for table scan, because it's more efficient to use column store, and TiDB can using a cost-based optimizer to like this part to go through the iFlash, whereas the index scan can be facilitated by the TiKV node. And this is what we call the smart selection based on statistics. And the iFlash is pretty easy to use. And if you deploy TiDB and then just alter the table and to include two TiDB replicas, two iFlash replicas, then under the hood, iFlash will start replicating data. And then once they are ready, then you can issue a query to both to use the power and combine the both data representations. And we do have some benchmark, and we see that this is for the on-time data, and we see that there are speed up compared with the Greenplum, Spark, and MariaDB. And on the TPCH, we do see some improvements as well in terms of latency compared with the Greenplum. And we do offer a TiSpark, which connects the TiKV to the Hadoop ecosystem. And the underlying data thing that TiSpark also knows about the transaction behavior of TiKV, and then it can get the transaction ID from the and when it starts querying, and then it using the current transaction ID to get a consistent snapshot of data across of all your data set. And also TiKV also has the capability of doing computation. For example, for aggregation, we can push down them to TiKV nodes. And this can also help iFlash to, so TiSpark to do faster queries, because we can push down the computation to the TiKV nodes. Okay, so if we understand the iFlash architecture, we know that a traditional data structure or infrastructure can be simplified by using TiDB together with TiSpark to facilitate the real-time like data processing, especially for speedy layer, because TiDB can support the application as well as provide real-time analytical capabilities. I hope this can, yeah.
Is this your last slide? Because
yeah, this is our last slide, yes.
Perfect.
Yes, I think I want to summarize a little bit. So basically, TiDB is a scalable database, and we have had many companies or many users to be able to scale their applications by using TiDB's scaling capability. And over the past 2 years, we also enhanced TiDB to add the analytical data capability, which means that you can not only use TiDB as your transactional or store to support the application, but you can also use TiDB to build more complex application, like modern data application, by utilizing its analytical capability. And we do see that there are already users are doing that at the moment. And if you are interested in learning more about TiDB, you can read about this blog. And also we have the paper already published and should be available for download soon. If you want to interested in trying out TiDB, and there's you can sign up for a free trial for TiDB Cloud, and it offers you a free credit for you to experience TiDB cluster for 2 weeks. And TiDB is also open source project, and if you are interested in contributing to the project, you can send a PR here. And we also are hiring and in the Bay Area, and shoot me a resume or apply here at the career website. And that's all for my talk.
Thank you. Hamid actually has a couple more questions. The first one is, are you versioning your data in both row and columnar stores?
Yes.
Okay. And then there was a follow-up to the question about when you when transactions get aborted and what happens with the records, if you would like to read that one.
Yes, that's true. So basically, so actually we have a transaction manager in both the row store and the column store. And what transaction abort in the row store, basically, you'll be marked as aborted, and then the data will not mark as committed, and the other transaction will skip the data and do some cleanup. And for the column store, we also have a transaction manager have the similar functionality and help to the rollback of the data. Yeah. Actually, we do that there in both the column store and the row store, so that to keep a consistent snapshot between to keep the data consistent.
I believe that makes sense. Hamid, did you have any, or anyone else have any other follow-on questions that you'd like to ask? Okay. Well, we'll keep this running for a little bit for people to ask questions. Thank you, Lituan, for the conversation and the talk about T-Spark and T-Flash and everything. What I would like to do now is quickly give one more announcement, which are I'm going to share my screen for a second if you don't mind. And oops, there we go. Hopefully you can see, we have 2 upcoming events coming up. Again, this is SF Big Analytics. Our upcoming events are on Tuesday, August 4th. We're going to be doing tools for machine learning interactive visualizations. And on Thursday, August 13th, the missing story of columnar format and Apache, I'm probably going to pronounce this wrong, Apache Kylan. I would like to do a couple of thank yous. First of all, I'd like to thank Eric and Lituan for the interesting talks that they gave today. I'd also like to thank Bill from AI Camp, who is actually the one hosting the Zoom talk. So thank you very much for allowing us to use your Zoom and give these talks. That is all I really have to say. If there are other questions that you'd like to ask either of our panelists, please do now. Otherwise, thank you all so much. Okay, it looks like there are no open questions, so I think we are done. Thank you, everyone, and enjoy the rest of your day. Oh, wait, there's one more question coming in before I say that. I thought oh, I'm sorry, I missed that. I apologize, Hamid. The question was, I cannot see the result of my updates in the same transaction on the column store side. And this is going back to his first question.
Okay.
If you look at all the answered questions, you can see the thread.
Okay. So basically that is done. We do replicate the uncommitted data. That is true, because that is for the ROP, because the replication is handled in rough layer, right? We doesn't have the doesn't aware of the transaction, right? So, but if you look at my slides in the iFlash diagram, let me share that again. How would that help? If you, sorry, that makes, I'm sharing the wrong one. Let me share the right one. Can you see my screen?
Yes.
Okay, thank you. Cool. There's a transaction layer, transaction manager here that makes sure that they are aborted. Because, okay, let me see this. So how does TiKV do transaction, right? So first of all, when we start a transaction, we get the timestamp and the transaction ID, right? Unique transaction ID. And then we write a write intent, which means that we know that the data is uncommitted, and this write intent will also replicate it to the iFlash layer, which means that iFlash not only have the data, but also have the transaction information, whether a transaction is aborted or they are in progress, right? Based on those information, iFlash can actually correctly discard data or commit data. Is that answer your question?
Anita, do you have any other follow-ups, or does that make sense?
I think the short answer is that the iFlash layer does has all the information about the transaction to handle this.
Okay. Great. And then are there any other questions that we need, or any other questions that people have? Okay, then I think we are done. Again, thank you very much, everyone. If you have follow-up questions, you can probably put them on the meetup in the comments, and maybe we can get some responses to that. And we will be sharing a recording of this event, and we will be sharing slides. So thank you.